Welcome Tim Vale from our solutions engineering team. Do we have a quick introduction?
Hey, Jim. Yeah, based in Atlanta, as you already said, I head up the sales engineering team here at Cockroach Labs. So great to talk about an exciting topic, truly exciting topic in distributed transactions.
Cool. Thanks for joining us. And then Andrew, welcome to your first webinar with the team. I love it.
Indeed, first webinar.
Awesome.
I'm Andrew. I'm coming to you from New York. I've worked on the transactional key value store for a couple of years, and I've kind of worked all around the product.
Yeah, well, honestly, Andrew, you and I started on the same day. So we're both November 5th, 2018. So we're about a year and a half in. Yep. Tim, you were very soon after, I think, or right before
December.
You were
2018, yeah. So a month later.
Feels like a lifetime, and we've come a long way. And you know, I'm excited about this panel. You know, Tim has a lot of really great experience working with our customers through issues that they have, setting up the database, thinking about transactions, thinking about latency around transactions, and resiliency of transactions, and resiliency of data, and how we just scale these things, and some of the unique capabilities that we're working on the front lines with, you know, configuration of the database. And in the meanwhile, you know, we have Andrew, who is instrumental in actually building all this stuff. And, you know, the software engineering feats that have happened within our team to actually make what we're doing work is phenomenal. I don't know, I've been in a couple pretty interesting companies. You know, I worked at CoreOS, and I think that was one of the best engineering teams that I had ever been involved with. You know, all the work that they were doing in Kubernetes and innovation around operators and all that. I think there's a whole lot of really interesting work happening within our team, and Andrew is a key piece of that, working within a whole group of some really interesting and amazing stuff that's going on. So, Andrew, thank you for joining and taking the time today, because it's, you know, if we're gonna talk about transactions, we got to get deep, right? Because it's actually the difference of what we've done here. You know, building a database to be ACID compliant is one thing. Building a database distributed is a wholly other level, and I think that's what we want to explore today. So I'll give you guys a softball to start. I'll get you going, Andrew, first. So, you know, we want to start this conversation. If we're going to talk about transactions, we kind of have to talk about what comprises a transaction and what is ACID. Let's just start with ACID. ACID's been around since 1983, right? Because the old is Jim Gray. So what just describe to us just ACID, and we're going to get much deeper, everybody. So we got to start somewhere though.
Right. So when we think about a transaction, we kind of need to define what is a transaction. And Jim, you introduced this concept, ACID. ACID is an acronym for atomic, consistent, isolated, and durable. And a transaction fundamentally is a set of operations which has these properties. So operations here, we mean like reads and writes and things that you do in a database. So I think the kind of really interesting ones that we're going to dig into are atomic and isolated. Consistency is sort of this interesting thing because people throw around this word consistency a lot. You hear about eventual consistency. And what's interesting is the term consistency, when you talk about eventual consistency, is actually somewhat different than when we talk about ACID consistency.
That's right.
ACID consistency is coming from this like database literature where people are worried about keeping different indexes and tables in sync with each other. Whereas the consistency of eventual consistency is really coming out of a distributed systems community where people are talking about, if I were to say do an operation multiple times, will I get the same result? Will I get a consistent result? So I think what's striking is that the term consistency out of that CAP theorem, eventual consistency world, is really covered by isolation.
That's right.
In our discussion.
Yeah, it's the I in ACID that I think is that's where the consistency comes in the conversations, really around the transaction side. I mean, consistency, it's like, yeah, our foreign keys sustain, like, you know, is the data, it's almost about the data integrity when you think about it from an ACID point of view, right?
Totally.
So, yeah.
Totally.
Tim, I mean, how much does ACID come up within the conversations you have and you know, just people thinking about workloads and transactions and that the isolation in ACID?
Well, it's funny, Jim. I mean, you know, it does come up a lot, but we talk to all sorts of different people in the meetings that we have. And we talk to, you know, it's kind of dyed-in-the-wool DBAs. We're very, very familiar with kind of the properties of a database and what it means. But we also actually spend quite a bit of time talking to application developers and architects. And for those folks, this might be something that they study up, to prepare for an interview question, but not something necessarily they think about each and every day as they're building applications. And I think part of what we spend time doing is really educating folks on the importance of not necessarily ACID in general, but I think kind of the key attributes that we're going to spend more time talking about today. Isolation, as it turns out, is a really, really important thing. And if it's not done well, and this was something I didn't really fully understand, and I've been building applications for 25 years, 20 years, and didn't have a full appreciation of, but isolation done poorly, or done, in a weak manner, can lead to all sorts of badness that can take a lot of time and energy and costs to discover ultimately, and can potentially cost you money. I wish, I guess maybe one way to answer is I wish more people had an appreciation for how important isolation is.
Well, it's so funny, Tim, because when I first started at Cockroach, I didn't know what a dirty read was, or phantom read, or right skew, and those were our conference room names at our first office, right? Weren't they, Andrew? I think, yeah, right?
Yep.
And yeah, and it was like, I didn't get it. I didn't understand like all the things that could go wrong with isolation levels, right? And so, Andrew, what are the different isolation levels, right? There's read committed, there's snapshot, there's repeatable read, and there's something we implement, which is serialized.
There are a lot of kind of arbitrarily termed ones. I know that there are some in the SQL standard. Kind of the weakest that I can think of is read uncommitted, which is just dirty reads are allowed. Transactions that haven't even committed. And then things get stronger from there. You have repeatable read, which indicates that your transaction will read values again. And I may be getting some of these terms wrong, in part because I tend not to concern myself with the weaker isolation levels. One that is seen as quite strong is snapshot isolation, where a transaction will be given a snapshot of the database from which it will read, and then it will apply writes. And even snapshot isolation, which is considered to be quite strong, permits this right skew anomaly that you brought up. This right skew anomaly that has been shown to be able to lose companies money. And so we can talk more about kind of how that happens and how we prevent that. And then kind of the stronger isolation levels, we have serializable, which is the default isolation level Cockroach supports. At least Cockroach supports something at least as strong as serializable. We kind of have termed our isolation level something somewhat stronger that we call no stale reads. But and then kind of the strongest in the world is strict serializability, which is serializable but also provides this total order according to clocks. As in, imagine the world did actually have a clock and everything occurred at a specific time.
We don't.
I mean, then in strict serializability,
there's not a sun in the sky, Andrew. I mean,
no, I don't want to get into the physics of it. Not that I'm an expert there either. But suffice it to say, there are a bunch of weaker isolation levels, and most databases default to those weaker isolation levels, including Postgres and MySQL, et cetera.
And I think, Tim, where I ran into problems as well, and I didn't realize I was doing something wrong, is that there are default isolation levels set in a database, and people don't think about it all the time. And it's not something you kind of think about, but then you start reading about what can go wrong, and what can go wrong with a right skew. Oh my God, that was the most horrible. Like, I just really,
it's weird.
It actually messes you up. Actually, it's a right skew, but it actually does the other thing too.
Yes.
From a system of record point of view, you're dealing with money, you're dealing with, things like this, it gets really interesting. Lots of things can go wrong in a database. So Tim, like, how often are you in these conversations about what can and can't go wrong? Do people really care?
Yes and no. I mean, at Cockroach Labs, we're working with all sorts of companies, large and small, and a lot tend to be in financial services, payment processing, where they come to us because they fundamentally understand how important data correctness is. And they really do have a true and deep appreciation for, isolation ultimately. But a lot of folks, as I said at the beginning, really don't know. I mean, again, I hope none of my former employees are on here, or employers are on here. But I mean, I built applications for 20 years, and what we were looking for was just, the fastest way we could access data. We didn't really care what the isolation level was, because we didn't fundamentally understand what could go wrong with weaker levels of isolation. And that was a really eye-opening experience.
Yeah.
One of I think that the huge breakthroughs with Cockroach is, we can offer these really strong guarantees, which ultimately means application developers have a heck of a lot less to worry about in terms of correctness, but we do so in a very, very performant way. So you get kind of the speed and the reliability and all sorts of other stuff I'm sure we'll talk about. But
and that's right, Tim. And a transaction isn't just a simple thing, right? Like a SQL statement and a transaction are very different things, right? And I don't think everybody totally gets that, right? And so just characterize, I mean, do you have conversations about this? There was a question actually, it just came in. It's like, how do we help developers actually understand isolation levels a lot more? We're doing that right now. Right?
Yeah.
You kind of got to get into like, you build a SQL statement, but that thing gets broken down into like transactions, right? Like it's like, and so do you get into those conversations as well, Tim? We're going to come back to you, Andrew, the distributed side.
We do. And I think, ultimately we'll get there, Jim. And I know you're kind of steering the conversation. So if I've jumped ahead a little bit, forgive me. But, one of the things I think is really important to understand about Cockroach is that we are fundamentally a distributed system.
Yep.
And so, it's one thing to kind of understand what a transaction is and why it's important in a monolithic system, but it's a whole other thing to really understand the impact of transactions when you're talking about a system that is comprised of many individual parts, all potentially processing different parts of the data that you're either, reading or writing. And so, the kinds of conversations that we get into with customers or prospects ultimately is, okay, I get it. I know what ACID is. I know what isolation, but how do you apply that to a distributed system? And where are the things that can go wrong? So we end up spending a lot of time talking about, what happens if this goes wrong or what happens if this fails? And it really all comes down to kind of how we have built kind of from the ground up this distributed SQL engine. Obviously, we're talking a lot about the transactionality of that system, but I think a fundamental understanding that you have to have when talking about Cockroach is really this idea that it is a distributed scale-out database that has all sorts of other properties, because it really, quite honestly, and Andrew can speak to this, it's made our lives a lot more difficult, right? I mean, it would be one thing to build a serializable, isolated database on a single node, but you deploy a database across 50 nodes that exist in different regions of the world. That's a whole other ball of wax.
That's right. That's right. And there's solutions out there that are kind of doing related typey kind of things. Like, I mean, look, Cassandra is a distributed system. You start thinking about transactions in Cassandra, that's a different challenge, right? I mean, because I think people think in SQL statements. Actually, the question's interesting. I was just thinking about this. Like, I think developers think in SQL statements. They don't think in transactions. A transaction is a bunch of statements, and a commit, right? Mm-hmm. Doing that in a distributed environment across multiple tables with data living all over the planet, not easy to do, right? I think if it was easy to build a database, I tell you what, we'd probably each build one for each one of our applications. It's not.
We know the other thing too.
Distributed is a wholly other thing, right, Tim? Yeah, sorry.
Yeah, no, and the other thing too is, kind of, do people think about distributed transactions? Well, you're right. I mean, what is a transaction fundamentally in SQL? It's that exactly what you said. It's a begin, it's an end, it's a commit. But certainly from an application developer, and I guess maybe I'm going to start talking about it more from this perspective, is application developers have gotten away from necessarily writing those things explicitly. A lot of the folks we work with are reliant on object relational mapping tools or other higher order frameworks in whatever language they choose. And a lot of those things kind of abstract away from the end developer the fact that there really is a transaction, that whatever it is they're doing against the database is starting with this begin and is ending with a commit. And so, again, we do spend a lot of time educating folks, hey, the things that you're doing against the database with Hibernate, for example, which is a Java ORM, or Juke, or, actually really does have transactionality, and you need to understand more about that.
Yeah, and let's shift into kind of the value of distribute as well, Tim. And I agree with you. I don't think developers think about these things, and I think that we've implemented serializable. I think that's the value of the developer ultimately. I think we've done a lot of the hard work in the back end to actually make this happen. And so, Andrew, I kind of mentioned building a distributed database is not easy to do, right? But there's a lot of value in doing it. What are the things that you think are the most valuable, from a distributed point of view?
Sure. I think that one thing, forgetting the fact that Cockroach can be applied in a global model, just the ability to scale out a transactional database is reasonably new in this world in terms of scaling out for both read and write performance. There are multi-master solutions out there that can provide relatively high levels of isolation within a single region, but they are often kind of glommed onto pre-existing database implementations. I think that providing a distributed database, which was kind of distributed first, gives you scale out with effectively no effort. And that's hugely powerful. The main reason people looked away from transactions kind of around the early 2000s was the need for horizontal scalability.
Right.
So I think that's a huge piece. And then what that comes to later is this ability to then provide geo-partitioning and global deployment topologies, which allow you to deal with regulatory challenges and provide low latency response times with strong consistency all around the world. And that makes it much easier to build an application that's serving markets kind of everywhere without needing separate operations teams, separate infrastructures. It can just be a huge cost saver.
That's right. I mean, it could be even a single data center, you know, like just the concept of sharding a database to me, it just seems like a nightmare. Like that's how we scale legacy databases. Like the concept is just so, it's just flawed because it actually takes, everything can go wrong. And I don't want to reshard the database, and I don't want to be the one up at 3 a.m. actually making sure the application is going to work with that thing. Let's just let the database deal with that, right? And I think it's kind of one of these, you know, I always have these very interesting conversations with Peter Mattis, our CTO, and like, you know, this concept, we have an internal thing is like make data easy here at Cockroach. And I think it's make data easy for the developer. Like, I don't want to deal with any of that crap, you know what I mean? like high availability, like, yeah, there's 2 data centers. Should people be deployed in 3? Like there's like just concept. I think it's a paradigm shift we're going through, you know, but it's a paradigm shift in the database itself, Andrew, right? So like there's huge, massive challenges doing transactions in a distributed environment, right? And so like foundationally, like what is like, you know, like the primitive number one we had to take care of when we start thinking about, you know, doing distributed transactions from a, you know, we're getting a little deeper now, right? Like let's get into layers, right?
That like at its core, the atomic commit protocol, this idea that you can have atomicity in a distributed environment is the kind of number one step to providing distributed transactions. First and foremost, a transaction to me is, because isolation is such a spectrum, durability is kind of a given. Consistency effectively doesn't apply. So atomicity is the beginning of a transaction. Atomicity is we take a group of operations and we make them one. And so I think at the very beginning, what you start with is the atomic commit protocol.
Yeah. And just explain what that means, right? Like,
right. So
in distributed, right? Yeah.
When you create a transaction in CockroachDB, and when you first perform a write operation, we create this notion of a transaction record. And that transaction record encapsulates the state of the transaction. And by the state, a transaction record will ultimately either end up as aborted or committed. Right. And once it becomes one of those terminal states, it will never become anything else. And I think that's the kind of fundamental concept on top of which transactions are built.
Right. And then there's, I mean, basically there's a state where something is being executed, right? And so there's a pending state. So like the atomic commit also allows us to actually deal with conflicts as well, right? And I mean, that's the big piece of that.
Absolutely. Yeah. So this transaction may be operating on one gateway node. It may have its transaction record on a completely different key value store node. It may then have laid down rights all across the cluster and all across the world. But the way that we coordinate between multiple transactions and the current transaction is through that transaction record. That notion of a singular record and being able to find that record in the cluster is what enables us to coordinate in a distributed setting. It allows us to have a single point where the whole system can rendezvous to determine kind of what is going on with regards to some transaction.
Right. Yeah, and I think it's a layer of understanding in the database that people typically don't understand. We just deal with this kind of stuff, and it's like the you said a couple things, Andrew. You said gateway node. You also said where the transaction is happening. just explain to the audience the difference between a gateway node and then basically everything from a SQL execution layer, just so it's really clear, because I think it's one of the coolest parts about Cockroach.
Right. So every Cockroach node runs all of the layers of the database.
Yeah. It's a single binary.
Are,
I don't have different types of nodes, right? Yeah.
Right. There's all of the nodes are all of the services, but there are layers. And so at the highest layer, I like to split it into two high-level layers. We have the SQL layer, which deals with client connections, parsing, planning, execution, metadata. That's where SQL lives. And all of that is implemented on top of a distributed transactional key value store, which has a much simpler data model. It doesn't know about tables. It just thinks in keys and values where everything is. But it's that transactional key value store that actually provides us with our transactional concepts. The operations at SQL become mapped to these key value store operations like puts and gets, et cetera. And the transaction is actually a key value store transaction. So clients can connect to any node in the cluster, and that node will act as the gateway with regards to SQL processing. It will manage the connection state for
the application, the request, right? Yeah.
Right. So the SQL driver has to speak this protocol that Postgres speaks that we've termed the PG wire protocol. And that's a state machine that's very tied to the SQL world. What also happens is we maintain a key value store transaction in that execution context of your connection. And that deals with all of the state management of the key value store operations, of dealing with issuing puts and gets, et cetera. What is then interesting is that the transaction record corresponding to the transaction state is unlikely to live on your gateway node, but rather will live in the key value store right next to the first write that you perform.
Right.
And I think that separation of the durable state of a transaction from the in-memory state of a transaction is an interesting and important point in understanding the architecture of Cockroach.
Yeah. Tim, did you want to throw in, I was going to ask Andrew about latency a little bit in the context of this. Did you want to throw anything in on that?
Yeah. No, I think Andrew did a superb job there.
These are really complex
these are
complex topics. I will say, if y'all want like a really deep explanation, our docs are awesome, and Jesse and that team do a phenomenal job describing some really difficult concepts. So we have gateways, we have a transaction, you know, and these things are happening, and a transaction can get distributed, right? Because a transaction, you know, between that begin and the commit can have lots of things going on, right? And data can live all over the place, right? And so what's the effect of latency between nodes, Andrew? Because we're talking about, I mean, this is a different layer of database. Like when we used to implement databases, I would think about the schema. I didn't really care. It was one name. Like now I've got to think about where the data is as well. Like how does that play into the transactions as well? And what do we do for that? You know, concerns around latency and network speeds and all that.
Absolutely. Unfortunately, the speed of light is not as fast as we would like it. In particular, humans kind of become aware of things at the, let's call it 10 milliseconds or tens of milliseconds.
Right.
And it takes much longer than that to go around the earth just once. And so sometimes a sequence of SQL statements might each require a round trip to some faraway piece of data.
Yeah.
And then it's if you don't plan out your network topology and your deployment topology well, your transaction, which comprised of maybe 7 simple select statements, is going to take a second because each one of those needs to go halfway around the world and back.
That's right.
Like that. And so you have to be somewhat careful in where you place data and how,
it's a key conversation we have. So Tim, can you talk about how we have that conversation with customers, right? It comes down to topologies and sizing of clusters, because it's not the biggest machine. Often it's actually the schema of the table, like, and how do you guys have those conversations, Tim?
Yeah, it's, you know, there's lots of different kind of things that we think about and talk about. And you've heard me say this many times. You know, one of the first questions we ask people is, what is it you want to survive?
Right.
And that really helps kind of set the bar for what it is we're trying to do. So if, you know, if you're not interested in surviving a cloud provider outage or a power grid failure, and you're more interested in, for example, in the cloud AZ type failures, we can begin to shrink kind of the size of the cluster topology, if you will, so we can kind of remove some of the complexities. But quite honestly, a lot of the folks that we work with are interested in surviving kind of very kind of far-reaching or severe sorts of scenarios. So we do have to spend time talking about how latency impacts things. Now, generally, there are lots of tips and tricks and dials and knobs that you can turn, but we do have to be aware of where data lives, especially for those topologies that want to survive things like regional outages or power grid outages or provider outages. These are real concerns for very large companies in the world that we're working with.
Yeah.
And when you do that, you have to be aware.
Yeah, and I think it's one of those key conversations. I think when I first understood the concept of the KV store underneath and how we use Raft within the database, it was really critical. And understanding primary keys on the table and actually understanding how that's going to help us geo-partition, which, funny enough, geo-partitioning comes up in our conversations and people are like, oh, wow, you can tie data to a location. That's a compliance thing. Actually, it was a speed of light thing, right? Like, it's there because we need to deal with this. Look at like our ultimate competition. I love talking about this. Our ultimate competition is the speed of light. Like, I think Andy Kimball, who's a senior member of our engineering team, I got up in front of the whole company one day and I think he just put the number up there. Wasn't that in a team meeting? He was just like, that's our ultimate competition, guys. So, yeah. But it's really tricky with transactions, but like Raft and how we set up the topology is actually really, really important. One of the questions that came in while we were talking, guys, is kind of related to this is, what happens when a gateway comes down in the middle of a transaction, or what happens when a transaction fails, or what happens when, a conflict comes in, right? Like I'm in Sydney, I'm in New York, same account, who wins, right? And so how does the database deal with that, Andrew?
Sure. So I think this all brings us back to this transaction record. The transaction record, in addition to including the state of the transaction, includes this heartbeat timestamp. And so the transaction coordinator is actually responsible for periodically pinging its transaction record. And when it pings it, it updates this timestamp. But if that gateway dies, then another node, which is perhaps blocked on some intent, which is a term that we'll introduce in a moment, it can take a transaction that is currently pending and move it to aborted, assuming that it has not been updated recently enough. Right. This allows the cluster to recover from gateway failure in roughly the window of the expiration of a transaction, which by default is 5 seconds.
Right.
So if you have a transaction that's written some data, and then you have another transaction which is also trying to write that data or read that data, it will block on the conflict and wait for the pending transaction to either abort or commit. And assuming that the gateway node, which had written that initial intent, dies, then we'll expire it and then move it to aborted and move on. So right. I hope that answers the question about gateway failure.
It does. Honestly, like we could talk about types of failures for about 4 hours, right? Like what can go wrong will, right? I mean, there's a lot of really weird corner cases that we've had to deal with, right? Like, absolutely. I think that's what's tough about a distributed system and these sort of things. Andrew, can you just talk about Raft and how that plays into transactions and what we're doing in Cockroach? Because I think our implementation of Raft borrows from etcd, which if people in the Kubernetes community are familiar with, the etcd Raft implementation. And so
I like to say that we share it with them.
We share it. That's it. Yeah.
We have about half of the commits on that implementation.
I know. It's great. And we're doing things like our implementation of Raft is actually doing multi-region and doing like what one would think would be a federated class. Like we're running into problems that other people haven't even ran into with etcd, right?
So we've actually implemented kind of what we sometimes term multi-Raft on top of etcd Raft, which is really a singular Raft group. In an etcd cluster, each node is a participant in just one Raft group. So nodes and Raft groups, they kind of go together. A cluster is a Raft group in etcd.
That's right.
In Cockroach, we are taking your data and storing it in this key value store. And so a key value store stores keys from 0 to FFFFF. But what we want to do is automatically partition or say shard this data dynamically based on your usage. And so we split this data into groups we call ranges. And
Yep.
each range you can think of as kind of an independently operating key value store. What's amazing and interesting to me is that the transactional protocol doesn't have any awareness of the fact that we're using Raft to replicate the state of the ranges. Say instead we had built the range servers to run just on very reliable hardware without replication. That would also be fine, and our transactional protocol would be interesting. But what makes it kind of more interesting is that we have this layer of high availability for each range that we get from Raft.
Right.
So what Raft ultimately allows you to do is have a set of servers act as though they are one server and have one piece of shared state. But they allow you to stay available even if n over 2 minus 1 of those n nodes is not available.
Right.
And so you get high availability from this use of a consensus replication protocol like Raft.
And we get quorum rights, and we get, yeah, I mean, it's just it's a critical foundational piece to distributed systems. And I think if anybody out there hasn't like actually read about Raft or gone through it, like it's again another one of these concepts. Like once you get it, it's like, oh wow, that's the paradigm shift.
Right. I think there's two layers here that you have to keep in your head. It's that you have this high availability due to the quorum rights of Raft for each individual range. And so for each individual range, any set of operations is itself already atomic because of the way that Raft works and our leaseholder system works.
Yep.
But then you have this transaction, which is about coordinating atomicity across different ranges. And I think that two-layer kind of architecture is the beauty of CockroachDB.
Yeah. And I think that's what makes it bulletproof and for these sort of things, and how we get to serializable and how you get to this reliable store that's multi-region, different parts of the planet. I don't know if we're going to get into parallel commits. I want to come back to something though. And there was a question, and it's actually a really good question. It was related to the failure of a transaction. Tim, what is the app like? Okay, so database is dealing with failures and all these things.
Yeah.
What does the application developer have to do to deal with this? Because there's going to be conflicts, right? There's going to be things go down. That's the whole nature of system. Things fail. Everything fails.
Yeah. So, again, this is part of my learning, from coming from building Java applications, as it were, against traditional relational databases. One of the kind of the key differentiators, I think, when building applications against a distributed system, certainly one that supports serializable isolation, is your database logic really has to, or your database access code really has to understand and be able to deal with retries or support what we call retry logic. And so, to answer Lewis's question here, what will happen under certain scenarios, and Andrew really kind of touched on a lot of these, is that if the database ultimately can't figure out the order of operations in a transaction, we will kind of defer back to the client. So we'll throw a retry exception and say, calling client, please restart or retry this transaction. And the calling code, the Java code or whatever other language you're using, really needs to understand how to handle these retry exceptions and ultimately resubmit whatever operation. So it's really easy to do. We've got plenty of examples in a whole bunch of different languages on our website. But I think the big thing here is understanding and implementing a concept of retry logic. I come from, or have done, a lot of Spring development, for example, Java and Spring development in my life. Spring, as part of the Spring project, there's an extension called Spring Retry, which makes it, if you're building like Spring-based microservices, using Spring Retry to kind of handle all this in a built-in way is just dead simple. And other languages and frameworks also make it simple. But the short answer here is understanding and supporting retry logic.
So I'll tell you, I was a horrible developer because I never wrappered anything, and I was really shit at commenting, and it was horrible. Tim, we also do something called select for update, right? And so that also helps you mitigate some of this. Can you guys, Andrew or Tim, can you guys just talk through that? Because I think it helps.
It absolutely can help. So select for update can prevent a large number of serializable violations because it will block conflicts which can occur. But it cannot prevent at least in today's implementation of Cockroach, all retryable errors.
Right.
It is true that select for update in other single node systems, which don't have to deal with failures, can mitigate most retry scenarios. So I think a key point here is that the need to perform retries is actually not fundamental to Cockroach, but rather is fundamental to strong isolation. If you run Postgres or you run any traditional database at serializable or higher, or well, effectively at serializable, you may encounter retry errors. There's a certain class of transactions where they're unavoidable. Imagine you have two transactions that are dealing with two keys. One reads key A and writes key B, and the other reads key B and writes key A. They can't both commit at the same time because they would violate serializability as a first-class concept. And so Postgres will also give you this serializable error. But as the commenter noted, select for update would prevent one of those two from making progress. And Cockroach, in its most recent release, does support select for update and can absolutely dramatically mitigate the number of retry errors.
Cool. That's really helpful, you guys. And I think it's I think there's some good best practice there. Wrapper things and use select for update, right? Like pretty simple from an app dev point of view. And I think it's really important. I come from, I was early days in the Hadoop world, and I understood MapReduce and distributed execution of things and all these things. How do we, what have we done special in our database, Andrew, from a distributed execution point of view? Because I think it's, again, like, look, I could take Postgres and put it on top of distributed storage, Aurora, right? Like, that's what they're doing. It's like, okay, you're distributed at one layer. Right. Distributed execution is totally different, right? And so why is that, special?
Well, in particular, one of the key advantages of MapReduce was this ability that you could scale out the computation such that you could utilize a large number of cores of machines to perform a single computation. And Cockroach's distributed execution framework is actually very akin to MapReduce in that it can ship the computation to the storage, which allows us to deal with speed of light delays by performing aggregations where the data is rather than streaming all the data back to the gateway, which is something that an Aurora or kind of shared storage based SQL server can't do. The basic idea is that we can compile our logical plan into this distributed execution plan where we can effectively build these MapReduce phases and perform a large amount of computation on remote nodes, and in particular co-locate the execution of a query on the node that stores the data that's being processed.
Yeah, I mean, why reinvent? Use that same sort of like concept, but actually build it into the database, which I think is like the critical thing here. And I think it adds a lot of things, right? Tim, I could see you. I mean, we're
actually, somebody asked a question that I don't know the answer to, and I really like to hear Andrew's perspective on this. I thought it was an interesting question. So Natalie asked, the underlying KV store is kind of foundational to Cockroach design. Did we begin with the idea that we wanted to have a key value store and then built a SQL layer? Or did we say we wanted a SQL layer and then we kind of figured out storage? I don't know that anybody's ever asked that question. I'm kind of curious what the what the rationale was.
Well, for a number of years after the Cockroach project started, there was no discussion of SQL. The SQL idea actually came a bit later. The original plan was to build this distributed transactional key value store, and it was an open question what the right API was. I think that Peter Mattis socialized the idea of utilizing SQL and building a fully fledged distributed SQL database something like 2 years after the project began.
I think he has a blog post on why we chose the Postgres SQL, right? I think it actually goes into some of that decision. So I was just gonna look for that and post it in the thing. So wow, you learn something new every day.
Hey,
I thought it was just
I know I do.
Way to go, Tim. Good question. Good question from the crowd.
Good question, Natalie. Thank you.
Exactly. So So another unique thing, and I know one of the people on our team actually put a link to. We just recently published a Sigmod paper. If this is definitely for this audience, if you guys haven't downloaded that, or y'all haven't downloaded it and checked it out, it gets into a lot of these concepts in a lot of detail. A lot of work went into that. So we'll dump that link into the general chat to make sure everybody has it. But we also, in that paper, we talk about parallel commits. We talk about cost-based optimization, and these are two kind of more advanced topics in Cockroach, Andrew, right? Like, and I think, building a cost-based optimizer in a single instance of a database is difficult. Doing it in distributed, taking the concepts of latency and location and all this stuff into, how much work have we done in there, and some general concept from the CBO.
We've done preliminary work there. We've done preliminary enough work that Cockroach is able to plan and choose different plans based on the data topology. And I think that's really critical. That's a next level concept that you may want to choose a different execution plan based on where the data lives. You'd rather ship computation across the ocean, even if, say, you're not going to be processing all that much data. In a traditional cost-based optimizer, you might only consider how much data is being read when making a choice about where to run or what sort of plan to choose. But we have now introduced the notion of latency into our cost-based optimizer, and that allows us to effectively choose a much more optimal plan in places where, say, you're joining against two tables which are known to be distant. I think that one really interesting result that we saw was in TPCC. You may be doing some cross warehouse joins or selects, and it may make sense to actually aggregate first on the per warehouse basis and then join, as opposed to vice versa. And that just the pure selectivity wouldn't have given you that plan. But once you take into account that some index join is going to need to cross an ocean, that it's obvious that you should do all of the stuff in say Europe that needs to touch data in Europe before joining it with stuff in the US.
And there's the whole side that's like heuristics around a CBO and like how that works, but then taking into consideration network speeds and like there's so much complexity that I don't think people really can actually be put into cost basing of queries. And I think that's a really interesting area. One last interesting area of execution I would want to talk about, Andrew, is parallel commits. That's something that we've done over the past year. We've been working on that for a year and a half, right? Can you just explain the concept? I have my version of it, but then again, I'm just a marketing guy,
So I think it's worth sort of stepping back and talking about how do you make a decision in a distributed system. And there's this classical concept of two-phase commit, where you're going to first kind of prepare and dedicate what decision you're going to make, and then after you are aware of after you've collected all the resources and told all of them, hey, don't change your mind, then after you can go back and say, great, now we're committed. And two-phase commit is correct and fundamental, and is sort of the old model of the transaction record of, we're going to write the transaction record. We're going to write all these locks that refer to the transaction record. We haven't really introduced this notion of an intent yet, but I think it's important to know that when a transaction performs a write, it writes out a provisional value where that row would go. And in that provisional value, it also puts a little asterisk that's like, this is provisional for this transaction with this transaction ID that you can find at this address. Right. And so, and that's one thing that was kind of brought up offhand, but we haven't really covered, is contention. And so when you encounter one of these provisional values, you'll then go to the transaction record that it points to and coordinate there. So the basic idea, though, is that we can flip a transaction from pending to committed once we have acquired all of our locks. That process is fundamentally two-phase commit. We lay down all the locks, that's phase one, and then we mark the transaction as committed. That's phase two. What parallel commits allows us to do is it doesn't actually change necessarily the basic concept of two-phase commit, but it allows us to change where the client observes two-phase commit. In particular, it says, let's be optimistic here. Let's issue all of these operations where we're going to mark the transaction not as committed, but as what we call staged, which is to say it is implicitly committed if all of the locks are successfully acquired. And in that staged transaction, we have a list of those locks. And so if all the locks do get acquired, then phase 2 will happen. And so long as we know that all those locks are acquired, then we can tell the client, hey, your transaction is committed. And this allows us to effectively take what was 2 round trips, acquire the locks, then do phase 2. Now we can just do everything in phase 1 and tell the client, hey, yeah, your transaction's committed. We'll go take care of moving it from staged to committed after you're gone, after you're happy, after you know that your rights are durable. And it effectively allows us to take these global transactions that used to take 2 round trips around the world and cut that in half.
Right. And if you think about the, the latency between New York and say Singapore, that's considerable. I mean, even New York to LA, like across the country, that can be substantial with multiple hops. And I always like to think about it. Look, we couldn't change the speed of light, but we could change the photons. Right? Like you can't beat the speed of light, but we can change what we're sending over. And I think that's, I think that was it's just phenomenal software engineering. And it took me a while. It took me a couple of reads on that RFC to actually sort the thing out. So Tim, how much are you getting into these conversations around latencies with customers? And do you get into conversations about parallel commits? I mean, are you getting into these layers of the transaction? Do people want to go there?
Yeah, they do. I mean, not everybody does, obviously, and we're in different stages and phases with different kinds of customers. And ultimately, these are complicated topics. These are detailed topics, and they're it really depends on who we're talking to. I've been kind of again taking this kind of from a developer perspective. Is this something an application developer needs to fundamentally understand with Cockroach? Not necessarily. You can use it, very well and very effectively without understanding it. But I think what we're seeing is that a lot of big customers in particular are building out, for example, CockroachDB as a service internally. And in order to do that, they want to have a really deep, detailed, fundamental understanding of kind of how Cockroach works. And so we do end up spending quite a bit of time, certainly with some of our larger customers, really understanding these finer points because it's important to them to ultimately support their internal constituents.
Right. And they're building so people are setting up as a service internally, easily build out next gen breakthrough apps.
Oh yeah.
As just giving this as their developers. So I was just looking through, we hit a lot of these questions, you guys.
I can cover a couple of them. I think there's a few we can get through quickly here.
Yeah, so you want to pick something off, Andrew?
Sure. So I may screw this name up, but Wazy asked about where the transaction record is relative to the transaction coordinator and the transaction gateway. And the coordinator and the gateway are the same node. The coordinator concept is really our code terminology for the key value store coordinator, whereas the gateways are contrived terminology for dealing with the SQL state. But the coordinator and the gateway are one and the same. And that is a distinct location from the transaction record. I hope that clears up that confusion. And then this last question from Jessica, how do you guarantee you'll get all the locks? Well, you don't. You do need to wait at the transaction coordinator for the responses from all of your initial requests to create these locks to come back before you know that a transaction is implicitly committed. What's interesting about parallel commits is the happy case is not actually all that complicated. As I described it, you know all the rights you've issued, and then as long as you get all the responses, you know whether they succeeded or failed. There are obviously failure scenarios, even with the coordinator not failing, where, I don't know, the server you're talking to crashes and you get an ambiguous result. And you have to deal with that. But the more kind of complex portion of parallel commits is what happens if you mark this transaction as staged, but then the transaction coordinator fails. Right. At that point, you have to run this recovery protocol where you go and query, well, did I succeed in getting all the locks? And it turns out that that's actually the bulk of the complexity in parallel commits. With regards to no stale reads, parallel commits has effectively, it in no way changes no stale reads. It's just somewhat orthogonal. The isolation mechanisms, which we haven't but barely touched upon, are pretty orthogonal to the atomic commit protocol. I hope that's helpful.
It is. And the original question, I'm sorry, I'm getting a little echo. Anyway, we got about 5 minutes. Tim, did you have any questions, or Andrew, is there anything else in here that you wanted to go through? I think we covered pretty much everything that's in here. We talked a lot about latency and network and its effect in transactions. The classing deadlock, I think we talked through that as well. There was that question as well.
It's kind of an interesting one just came in about how we compare with Postgres.
Tim, you want to take that? Yeah. And
I mean, I think, if we think about like isolation, Postgres, I do believe ultimately can run with serializable isolation. What we have observed is the performance isn't all that great, certainly relative to running in weaker levels of isolation with Postgres, but ultimately Postgres does support serializable isolation. It just would not be in a distributed fashion like we are.
Right.
And then,
and then I mean, the other side of it is Mongo and their isolation level, and that's actually, I like to call it casually consistent.
Oh, we have Jessica has reminded us. Is Jessica a plant for us? Who is this? Because she's asking great questions.
I know.
She's not a plant, is she? She's not. We don't have such a thing. Whoever you are, great question. Yes, Jepsen. Let's talk about Jepsen.
We got a little bit of time.
We got 4 minutes, right?
Last time we did a Jepsen test, I think was what, a year and a half ago, you guys? 2 years ago?
I don't know that we've actually had Kyle since maybe 2017 or 18.
Yeah.
We do run on a nightly basis the full suite of the Jepsen tests. And we've set up a few others to kind of speculatively test areas that we were just kind of interested in. So Jepsen is this framework for issuing queries in a concurrent environment and then evaluating the query history to determine whether there are observed anomalies or failures. It's a very powerful tool for correctness. If we had one complaint with it, it would be that it's relatively low throughput. It doesn't actually run at all that high of a throughput or concurrency. I know that there's this really cool new workout from Kyle called Eve, which is a much higher throughput evaluation framework that utilizes exploring the MVCC history exported by the database. And I would love to get him on board. I guess I might ask, what more specific questions do you have with regards to Jepsen?
Yeah, I think part of it is like it was advertised in the original kind of push of this session, and I honestly, guys, I lost a little bit, lost track of time in the concept itself. We ran the Jepsen test in 2017. I think we've actually dealt with a lot of the things that were found in that analysis, and we'll probably go through this again within the next year or so. As we see a major release, but we're doing twice annual release, right? So we're 20.2 will be here in the fall, and then 20.1 will be 21.1. That's going to be a fun one to say. We'll be in the spring next year, so we'll go through that again. So, but yeah, we're running it nightly. We run a whole bunch of tests every night, testing all this stuff. So, well, guys, we have 1 minute left. Let me see here. Is there anything easy we can pick off here?
Kind of just running through. I answered one about essentially quorum on multi-region rights. I think we've handled Jepsen.
Okay. We'll go through. I guess we'll go through this. It is the top of the hour. I want to be respectful of everybody's time. So it is 59 minutes past. So, Andrew, Tim, thank you guys for joining and doing this. You guys are awesome. And Andrew, the level of detail is just phenomenal. And Tim, your experience is really great for everybody to hear that stuff. So, and I love, this is like the view of Andrew's keyboard, basically, y'all. Like, it's great. Like, so everybody who joined us today, thank you for taking your time. We hope this was valuable for you. Please do give us feedback. I think there's a survey that goes out afterwards. We're going to do another one of these. I think it's in 2 weeks. We're going to actually have a member of the GCP team The Google team is actually going to talk through the results that we had testing their platform, their hardware, as part of our cloud report, to talk through kind of, how do you optimize GCP for, whatever workloads you are from a hardware point of view. After that, we're going to talk about these topologies a little bit deeper. We're going to have a member of our docs team. I think Jesse's going to join me for that. And then, to follow up on the Jepsen thing, I'm really trying to get Ben Darnell, who is one of our founders, on this show as well. And I think that's a great topic for Ben. I know it's very near and dear to him as well. So we have a whole list of these. I hope again, please, if there's any feedback, comment, criticism, improvements, please do give that back to us. But I hope this was valuable to everybody. Tim and Andrew, thank you. So goodbyes.
Thanks for having me.
Bye now. Thank you.
All right, everybody. Thank you very much and have a great day.